All right, good morning, everyone. Uh, Please let me know if you are able to see my screen.
Good morning, sir. Yes, we are able to see.
Okay, fine. Thank you. All right, so today we will get started with generative adversarial networks or GAN. So GAN is essentially another type of generative model that we are going to study today, and the next week. So we'll need two sessions for this at least. Okay, so this is the uh, this is our usual diagram that we refer to, and what we have done till now is essentially we have studied about autoregressive models. So we all know the usual story. The usual story is that we have access to some samples from the true data distribution. And then we have a model family, which is usually represented by a neural network whose parameters are theta. We optimize the um, neural network to come up with a probability distribution that is as close as possible to P data. Okay. And there are various techniques by which we do it. One of the key techniques that we saw is KL divergence. Okay. And for doing each of these particular things, for working with KL divergence and whatever we have done till now, so let's just build up the story a little bit. So what we did was the first class of models that we saw was autoregressive models, which is sequential in nature. And this particular probability density is represented by the chain rule, which is nothing but a product of the factors of the product of the conditionals. Okay. And then we came to variational autoencoder. It was like a big mixture model uh, where where we essentially calculated this probability density. And then we saw another type of model, which was normalizing flow model, which was kind of like variational autoencoder, but the thing is that we had direct access to the likelihood, and it was deterministic in nature. Okay. And in all these type of problems or class of models, in all these class of models that we have discussed till now, the key thing that we have done is minimize the KL divergence. Okay. Or equivalently maximizing the likelihood. So what we have done till now is in all of these models, we either had direct access to the likelihood. For example, you had your autoregressive models and the normalizing flow models, or somehow you took a workaround where even though you don't have direct access to the likelihood, but you have access to some other parameter like elbow, which is the lower bound onto the likelihood. But either way, we were working with likelihood, and we all know that minimizing the KL divergence is equivalent to maximizing the likelihood, and that is why we took this particular approach. Okay. Now, all these worked well because we had direct or indirect access to likelihood. Um, but the key story that we are going to build up today is we are going to change this. We are going to change this. All right. How we measure the performance. And the key um, reason why we want to change these is because if we do not use likelihood based models, we will get much more flexibility in terms of the design that we are going to do. And we'll see how. Okay. So this is the quick background of what we will be starting today. And so the next thing that we must understand is why did we use maximum likelihood? Okay. And this is a very key question of why we wanted to use maximum likelihood. So if you see here, I mean, this is our training set, x1 to xm. Okay, they come from an unknown true distribution, which is p data. Okay, so it means that we have data samples from x1 to xm drawn from a true unknown distribution p of data x, right? That's what we have. Then what do we have? We also have a model distribution, which is represented by p theta x, and this is basically parameterized by theta. Okay, so what we would do is we choose this quantity, which is theta hat, theta optimum, okay, such that the model assigns maximum probability to the observed data. This is nothing but your log likelihood. That is what is likelihood, maximum log likelihood or maximum likelihood. Okay. So maximum log likelihood is equal to what exactly it is equal to? It is equal to making the observed data as likely as possible under the model. Okay. So what is maximum likelihood? Maximum likelihood is making the observed data, these data, as likely as possible under the model, which is represented by p theta. Okay. Now, this is the story of maximum likelihood. Now, there is a reason why we use maximum likelihood. The reason is that if you had a model which was rich enough, I mean, very powerful model, okay, to represent the true data distribution, then there would exist a unique theta star, okay, that satisfies this. That means my p theta is going to be exactly equal, not approximately, exactly equal to p data. Okay, so we have, we assume this is an ideal case, okay, not a real life case. We assume this is an idealized theoretical assumption. So we assume that if we have a model which has sufficient capacity or it is rich enough, then it is always possible to get to the true unknown distribution. Okay. And the reason why we use maximum likelihood is because that the among all the type of different models which are available, I mean, different type of techniques which are available, maximum likelihood is the fastest in convergence among all the statistical method. Okay. It means that under a certain amount of, whenever you have certain amount of data, if you use maximum likelihood, you are guaranteed to reach the convergence faster. It means that you are going to use your data better. Okay. So what exactly, I mean, what exactly you mean by optimal statistical efficiency? It means that if our model is correct, okay, if our model is correct, that is the base assumption. We are assuming that our model is correct. It has sufficient capacity and all those things. Okay. How that is possible, that is a different story. If our model is correct, maximum likelihood learns the true parameters as fast as theoretically possible. So as the number of samples goes towards infinity, it means you have infinite number of samples. As the number of samples increase, your theta hat tends towards theta star, which is essentially, this is no longer an approximation. This is no longer an approximation, but it is an exact measure. Okay. And the rate of convergence is optimal. So you understand one particular thing. Whenever you are using any statistical tool um, to find out a statistical parameter, okay, you well understand that the quantity that you are calculating, the quantity that you are calculating will not remain static. As the number of as the number of samples increase, let's say we are talking about sample average, that's a statistical quantity. The sample average will also hover. Okay, the sample average will also hover, and finally kind of kind of what you call because of the law of large numbers, it will kind of stop hovering. Okay, and it will get fixed somewhere. And if you see the variance across all these, as you increase the number of data points, what you are going to see is among all these statistical tools that are this, the rate of convergence of maximum likelihood, or that is the variance shrinking of the data, is optimal. Okay, that is the reason why we use maximum likelihood. Okay, one of the reasons. And when we say that this is the fastest among all, okay, fastest does not mean faster training time, and it does not mean faster optimization per iteration. It means that with the same number of samples, in samples, ML essentially gives the most accurate estimate possible. That is what essentially it means. Yeah. And the second point, the first point we have discussed in detail. The second point is higher likelihood is equal to better lossless compression. And this is exactly what we discussed earlier as well in detail when we were talking about entropy, information, and all those particular stuff. So here, here we all know that in the context of data and models, the likelihood of data is how probable the data is under a certain model, right? So if I have to just let me get a uh, just let me get a blank slide. Okay, so when we say likelihood, likelihood is what? Probability of the data given the model. This is likelihood, right? So if our model essentially assigns high probability or high likelihood to the actual data, the model is very confident in predicting or describing the data. That's the key thing, right? So what we are saying here is that higher likelihood is equal to better lossless compression. What do we mean by lossless compression? Now, from our detailed discussion on entropy and information theory and all those things, you remember that lossless compression, when we said that essentially, if we have an if we were to if the probability of an event is high, it means that we need less information to store the event, less information to store. Okay, the less number of bits to store. And if the probability is low, we need more number of bits to store, or it has higher information content. Okay, so essentially, that what does it mean? It means that higher probability translates to fewer bits needed. Okay, so when we are talking about compression essentially encodes data without any loss of information, right? The idea is to represent frequently occurring patterns in fewer bits and rare patterns in more bits, right? Because of high probability, because our event is highly probable, we need we can predict it easily, and that is the reason why we need lower bits or fewer bits of information. However, if our event is rare, we need more information and we need more bits. right? So these encodings are usually done by various techniques like Huffman coding, arithmetic coding, and all those particular stuff. And we know we have discussed in detail that information is given like this, right? And then we have entropy and all those particular stuff. So what it is, what this lossless compression is saying is that if we have a high probability event, if we have a high probability event, or if we have a higher likelihood, it means the compression is better and we have a lossless compression, right? So if our model assigns high likelihood to the data, it means that the events and the data points are more expected, right? That's what it is. And therefore, the model can encode them in a fewer number of bits. And hence the model is more, the key thing is that model is more compressible. Okay. So the key thing to note here, the key thing to remember here, and it's not only about remembering, it's about understanding, is that higher likelihood translates to lower entropy, right? Randomness is less, fewer bits, and better compression. This is the moral of the story. Okay. So if I have to go here, it means that, so now the question that comes, next question that comes to our mind is the likelihood a good indicator of the quality of the samples generated by the model? Now, ultimately, we are in the generative space. We are in the generative modeling space. Deep, we are talking about deep generative models. We will sample images, right? If we talk about images. Now, can we conclude that likelihood is a good indicator of the quality of the samples generated, right? Ideally, whatever we have studied till now, ideally it should be, right? Because if you have if your likelihood is high, it means that, I mean, the quality of the samples generated are closely corresponding to the training data and all those particular stuff. But that is a question that we need to answer. Okay. Now, let's try to answer this particular question. Case one is optimal generative model will give the best sample quality and the highest log likelihood. Okay. So what it is saying is that if this particular quantity D of P data and P of is exactly zero, okay, it means it is exactly zero. Your model distribution is exactly equal to your data distribution, very, which is rarely the case, which is never the case rather. Okay. In that particular scenario, your sample quality, I mean, your generative model will give the best sample quality. Okay. And the highest log likelihood. And this particular correlation between log likelihood and sample quality will basically hold true. However, in real life, what happens is your P data approximates your, sorry, P theta approximates your P data, right? We never have a model which is perfectly the same as your P data. So this is an imperfect model. I mean, your likelihood may be very close to the likelihood of P data, but it is still an imperfect model. Okay. And experimentally, it has been shown that in such cases, Achieving high log likelihoods might not always imply good sample and vice versa. Okay. So we will talk through it. We will talk through why this is the case, and we will kind of we'll kind of derive the same thing as well. Okay, so this is the first case. Now, when we talk about this first case, let's see why we say so. Okay, why we say so. So the question that we are trying to answer is why log likelihood is not always a reliable metric of sample quality. This is the question that we are trying to answer. Okay. To answer this particular question, what we will do is we will take a model. Okay, p theta x is equal to 0.01 p data x plus 0.99 p noise x. So this is a noise dominated mixture model. Okay. Now, in this particular thing, you see that only 1% of the time the data is coming from the true distribution, and 99% of the time the data is coming from a noisy distribution. So 99% of the samples come from noise. So 99% of samples come from noise. Okay. Now, this is my model. Now, what I want to do is the first case that I'm going to do is I want to calculate the log likelihood lower bound. Okay, log likelihood lower bound. Now, to calculate the log likelihood, what I'm going to do is I'm going to take the log of this particular equation. So this becomes log e theta x. This becomes log of 0.01 p data x. Sorry, bracket will now close here, plus 0.99 p noise x and this. All right. Now, we can, from this particular thing, we can easily say that because log is increasing and monotonic, we can easily say that log of p theta x will always be greater than the log of any part of the sum, right? It will always be greater than log of any part of the sum. Okay. So then we can easily say that log of p theta x is greater than equal to log of 0.01 p data x, right? We can easily say. And this particular term here can be written as like this: log of p data x minus log of 100, right? What have I done here? Nothing, right? I mean, I have just expanded this product. Log of product is equal to the sum of logs. That's what I have done. So what happens here? It will be when I take the product, when I convert it into a sum, what will happen is log of p data x, and then the other quantity is going to be log of plus log of 0.01. Now 0.01 I can write as log of 1 by 100. And if I simply flip the sign, and then it becomes minus log of 100. This. Okay. So now this particular quantity, log of 100, is 4.6. Okay. Now, what do you understand from this particular equation? You understand, you should take from this particular equation is log of p theta x is going to be greater than log of p data x minus 4.6. And what has happened here, if you see, if you just logically think about it, that even though 99% of the model is junk, okay, its log likelihood is still only 4.6 units worse than the true log likelihood, right? True data log likelihood. So you see that even though with 99% of the model was noise, the lower bound that we have found says that my log likelihood can still be only 4.6 units worse than the true log likelihood. So the margin is very narrow. Okay. Now, okay, let me get a couple of pages. Okay. So this is the first thing that we did. Okay. Now, what we are going to do is we are going to calculate uh, the log likelihood upper bound. Okay. Now we know that KL is given by this DKL P data P theta is equal to expectation of P data log of P data x divided by P theta x. Now, from our knowledge, we know that KL will always be positive or 0 if essentially P data is equal to P theta. Right? That's what we know. So now if we expand this particular equation, what will happen? So we can write this equation like this, DKL. I'm not writing the entire thing. Okay. DKL is equal to expectation of P data, expectation of P data into log of P data x minus expectation of P data log of P theta x. We can write it like this, right? I've just expanded this particular thing. Now, since KL is always going to be greater than or equal to 0, we can easily say that this quantity, which we have said, all right, this quantity will always be greater than equal to 0, which means we can write expectation of P data log of P data x is greater than equal to expectation of P data log of P theta x. We can write it like this. So it means that, so now we know that the log likelihood under the model distribution, I'm closing this, the log likelihood under the data distribution is always greater than or equal to the log likelihood under the model distribution, right? So we have this particular scenario now. And now I create the sandwich. Okay. Now I'll create the sandwich, which is basically the lower bound and the upper bound. Okay. So how do I do it? I first take the lower bound. All right. I first take the lower bound. What was the lower bound? The lower bound was this. Sorry. This is this. Now, here you have an expectation everywhere, right? So I'm going to take the expectation of this. So if I take the expectation of this, it is going to be expectation of P data into log of P theta x is greater than equal to expectation of P data into log of P data x. And this will be log of 100 because it's a constant. All right. Now, if I combine this particular thing and this particular thing, what will I get? The thing that I am going to get is essentially this. Expectation of P data log of P data x minus 100. So minus log of 100, sorry. Log of 100 is less than equal to expectation of P data log of P theta x is less than equal to expectation of P data log of P data x. And see how beautiful this equation is. Right? So now what happens is this quantity which you, sorry, this quantity, this particular quantity which we were talking about, okay, is at most equal to this, all right, or less than this, and this will be greater than this. Okay, what does this mean? This means that this is the sandwich. The model's expected log likelihood is squeezed between the data log likelihood and just 4.6 units below it. Right? So even if the model, P theta is mostly noise, 99%, which we took, the log likelihood looks very good. Okay? Because it is not much worse than the true log likelihood. And this essentially shows that high log likelihood is not a guarantee of good examples. Okay? Or rather good samples. Okay? And if you take the case of high dimensionality, I mean, what happens? So if the dimensions are very high, the log likelihood remains great. Okay. And the noise penalty becomes negligible per dimension. Right. So there will be a model which is very close to P data, but still producing bad samples, especially in higher dimensions. Right? Because the penalty that we are getting, I mean, this particular thing, if you divide it by a high number of dimensions, it becomes very, very negligible. Okay. So this is essentially why higher log likelihood does not always guarantee uh, good samples, because the model that we will be training will never be exactly the same as your true log likelihood model. It will be only an approximation of your log likelihood model. Now, any questions on this? Okay. All right. So this was the slide. Uh, you can go through it. We will talk through. Okay. And next case is, all right. Next case is, can you think of a model which is giving you grades? Can you think of a scenario which is giving you great samples but poor log likelihood? Any answers? So the question is, you have a model which is giving you great samples, okay, but the likelihood is poor. What can be a scenario in what can be one of the scenarios here? Can you think about anything? Anyone wants to take a punt? Okay. So you remember when we talked about overfitting, what did we say? Overfitting, in case of overfitting, and what happens? The model is much more complex. We have lesser amount of data, or our problem statement is simple. Well, and because the model has so much of freedom, what essentially happens is the model memorizes everything and gives you very good result during training. But during validation or testing phases, it falls flat on its face. Okay. Now think about this particular scenario here. Great samples, poor log likelihood, memorizing training data. So this is an overfitting case. So even in case of overfitting, you will see that your model is giving you grades. So the earlier case was good log likelihood, poor samples. This is basically the reverse case. Great samples, but poor log likelihood. And now you see that the test set has zero probability assigned to it. Okay. So the whole discussion for the last 45 minutes is revolving around the fact is the above cases suggest that it might be useful to disentangle likelihood and the sample quality. Okay, and that brings us to this particular topic, which is likelihood free training. We don't want to access the likelihood, even though we may have access to the likelihood, but we are not interested in accessing the likelihood. We want to go for a likelihood free training and consider alternative training examples, basically, that do not directly uh, depend on likelihood. Okay, so this is the whole story why we want to go for a likelihood free training. So we started by saying that whatever generative models we studied till now, they either had direct access to the likelihood or indirect access to the likelihood, right? But we now wanted to delve away from likelihood based training. And the reason we wanted to delve away from the likelihood training is because likelihood, particularly, even though it is the best statistical tool or to basically do the training with a certain amount of data, it will give you the best possible convergence. But the problem is likelihood and your sample quality are not all tightly coupled. Okay. And the reason we saw is that very less penalty that we have, which is 4.6. All right. And that is the reason. Okay. Now let's move towards likelihood free trading. Now here, so obviously when we say we want to move away from the likelihood trading, every component remains the same. We have our neural network here. We have our P of data here. We have our samples here. All these things remain the same. The only thing that we can play around with is this particular thing, which is your performance measure. Okay. And we want to now go for a performance measure which does not deal with likelihood or log likelihood. Okay. So how do we go about it? So the way we are going to go about it is essentially that we are going to have two samples. Okay. We'll compare the distributions via sample. So we are going to have two set of samples. Okay. S1 comes from a distribution P. S2 comes from a distribution Q. Okay. And just leave the true distribution and the model distribution and all those particular stuff for the time being. Just concentrate on this, that we have two separate distributions, and we are getting samples from P, and we are getting sample S2 from Q. And given a finite set of samples from the two distribution, how can we tell if the samples are from the same distribution? Okay. Now, the key question is, if I pick up an image from sample one, from distribution P, if I pick up a sample S1 from distribution P, and if I pick up a sample S2 from a distribution Q, and if these two samples look alike, that means that both my distributions are same. Okay. And I'm not talking about one sample, I'm talking about multiple samples here, finite set of samples here. Okay. So if we are able to do this, that means that both there is a fair chance that both the distributions are same. And that is the philosophy with which we are going to approach this likelihood free trading. Okay. Now, what we are going to do here is we are going to have a two sample test. Okay. It's a standard statistical test that you have for those who have taken statistics class. Okay. So we have this S1, which comes from P. We have S2, which comes from Q. And the two sample test considers the following hypothesis. You have your null hypothesis, which says that P is equal to Q. And you have your alternate hypothesis, which says P is not equal to Q. Okay. We want to design a test statistics T to compare S1 and S2. Okay. And these test statistics can come in various uh, uh, can be of various forms. Okay. You can compare the mean of two distribution. You can compare the variance of two distribution, and so on, so forth. Okay. So in this particular case, what we are doing is we are basically comparing the mean of the two distributions. Okay. And what we are going to say is that if T is larger than a threshold alpha, then reject the null hypothesis. Otherwise, we say the null hypothesis is consistent with the observation. Okay. So the key thing here to note is that likelihood free trade, test statistic is likelihood free trading. So there is no likelihood here, right? We are just taking some test statistics here. This is likelihood this because it does not involve the densities of P and Q. Okay, that is the key thing. Now, to do this kind of uh, testing, what do we need? The first thing that we need is your direct access to your P data. This is always available in the form of your data set or your training data. So you have your P data, and from this P data, there comes the training data set. Okay, so you have your samples. Then you have some model, and that model is such that it permits efficient sampling. So you can sample from that model as well. Okay. So now you have two set of samples. One that is coming available as your training data coming directly from your true data distribution, and the other which is essentially coming from your model distribution, provided that your model distribution allows efficient sampling, which we'll ensure during the design. Okay. Now, can we train a generative model to minimize a two sample test objective between S1 and S2? That is what we are going to do. Okay. Can we train a generative model to minimize the two sample test between S1 and S2? And that is going to be our alternative notion of distance between the distribution. So that's how we are now not venturing into the likelihood zone or the probability density zone. What we are trying to do is take the samples, do a two sample test, which is independent of your likelihood or your probability density, and trying to compare both the samples to see if both the samples look the same. And if all these samples look the same, that means that they come from the same distribution. And that's how we are going to move forward. Okay. All right. Any questions? Sorry. Okay. I mean, if anyone wants me to repeat anything, I can do so. All right. We have time. If someone did not understand anything, and I can basically do another round for that particular concept. Okay. All right. So what we are going to do is now, what did we say? We said that we will do a two sample test. We will do a two sample test. All right. We will do a two sample test. Now, during the two sample test, we saw two test statistics that we kind of hand designed. Okay. One was we saw that we could, I mean, we just took two arbitrary examples. We said we can compare the mean of um, two distributions. We said we can compare the variance of two distribution, and there are various other measures that can be done. But hand curating two sample test objective in high dimensions is very hard. Okay, it's a hard problem. Why? Because if you see here, if you see this particular diagram here, these are two Gaussian with different means. Now we are taking means. Okay, let's say our test statistics is comparing the mean of two distribution. Now we see that the two distributions are different because the mean is different. Easy problem. But then when we go across many scenarios, we find that there can be two distributions which have the same mean but different variance. What do you do then? Then there another dimension comes in, right? Then along with mean, I have to take the variance as well. And then if you solve this problem as well, you will find that there are various kinds of distributions, for example, Gaussian and Laplace densities, where your mean and the variance is the same, but their shape is different. So it's a problem which is, I mean, which you cannot get your hand around. Okay, you cannot solve manually. You cannot hand curate this kind of test statistics. What you have to do is you have to learn a test statistic automatically to identify in what way the two samples of S1 and S2 differ from each other. And how do you do it? We do it using a classifier. For example, you have a binary classifier. What does a binary classifier do? You studied in logistic regression, right? What does it do? You have an apple and orange, it says whether it is an apple or an orange. It just classifies, simple, right? This particular classifier, in terms of GAN terminology or GAN literature, is called the discriminator. Okay, so the first component that we are introducing here is called the discriminator. And we need the discriminator so that we can say, we can discriminate between the sample S1 and S2 coming from two different distributions. Okay. All right. Now, the question is, this particular discriminator, D phi, is basically nothing but a neural network, where phi are the parameters of a neural network. All right. Now, what does it say? It says that any binary classifier D phi, which is neural network, which tries to distinguish real, that is y is equal to 1, samples from the data set and fake y is equal to 0 samples generated from the model. Okay. The key thing to note here is this. Test statistic is equal to minus loss of the classifier. And I'll come to that a little bit later. Okay. It means that low loss, if you have low loss, okay, real and fake examples are easy to distinguish. If you have high loss, it means real and fake examples are hard to distinguish. They are similar. And the goal is to maximize the two sample test statistic in support of the alternate hypothesis, which is this, which proves that P data is not equal to P theta, or equivalently minimize the classification loss. Okay, this is the discriminator. Now, the key subtle change here is that because we are trying to prove the alternate hypothesis, that is P data is not equal to P theta, we are going to take the negative loss of the classifier as our test statistic. Okay. And why do we do that? Let me take a. Okay. Why do we do that? All right. So we are using a classifier or a discriminator to compare the two distributions. So the first case is low loss. What does it mean? From all our knowledge of machine learning, we know that the classifier does well. And if the classifier does well, it means it is able to distinguish between the two samples, and that means the distributions would be different. What is the second scenario? The second scenario is high loss. In the high loss, the classifier is confused. And it means that the distributions are same. It is not able to distinguish the sample 1 from sample 2. It is confused. And our goal is to maximize the confusion of the uh, discriminator. Okay, so that it is maximally confused and we know and if it is no longer able to distinguish between the samples of the two distributions, then it means that both my distributions are same. Okay, now what are we doing for this? We said that we are going to do a two sample test. The two sample test says that your null hypothesis is equal to p data is equal to p theta, and your alternate hypothesis is p data is equal not equal to p theta. So from our statistic knowledge, we know that to support the alternate, we need a test statistic that is larger when the two distributions are more different. Okay, and gives stronger evidence against the null. So two conditions. The first is test statistics test statistics is larger when the two distributions are more different. And number two gives stronger evidence against the null. Okay. This is the exact reason why we flip the sign. Why this happens. Why we flip the sign. If we flip the sign, what happens? A, A, if classifier loss is low, it means that it is a good discriminator. The test statistic is high. Okay, and the evidence is that the distributions are different. And the other case is that if the classifier loss is high, it means that it is a bad discriminator. Test statistic is low. And it means that it is the sample is different, right? So that is the reason why we need this. So what are we doing? I mean, without going into all these complications, the simple thing that you should remember is the first component of a GAN is a discriminator. And what would the discriminator do? The discriminator would take two samples, one from the true distribution and one from the model distribution, and then basically try to compare them. And somehow my goal is such, and we'll see how we achieve the goal. Somehow my goal is such that if my discriminator is maximally confused, it does not know which one is true and which one is false. I mean, which one is a true sample and which one is a fake sample. That means both my distributions are same and my GAN has done a good job. Okay. So let's move forward. Now here, this is the training objective for the discriminator. Now, before I go into anything, one thing that you need to keep in mind is that GAN has two parts. One is the discriminator, and the other, which we have not talked about as yet, is the generator. Okay. And these two are playing a game. Okay. The game is that the generator is going to generate samples from the model distribution. Okay. True distribution you already have. Okay. You don't have to generate anything or sample it. I mean, you don't have to basically generate any samples. The generator generates samples from the model distribution, gives it to the discriminator. And the discriminator says that this sample is different from true data distribution. So the goal of the generator is to fool the discriminator. And the goal of the discriminator is to basically tell the generator that the samples are not correct. I mean, samples are not matching. So if my generator, and this is basically the training. So this is the iterative training that is going to take place. So the generator, every time the generator is going to generate something from the model distribution, it is going to give it to the discriminator. The discriminator already has access to the true distribution. It is going to check both the samples. It's a classifier, nothing more than that. And it is going to say that whether it is whether both the samples are similar, same, or they are different. Now, as long as my discriminator is able to distinguish between the samples coming from the true distribution and the samples coming from the model distribution, that means both the distributions, that is P and Q, which is essentially your data distribution and the model distribution, are not the same. But after a lot of training, after playing this game multiple times, after a lot of training, if my generator is able to fool the discriminator and the discriminator is no longer able to distinguish between the samples coming from the model distribution and the samples that we have access from the true distribution, that means both the distributions are the same. And that means that my, my model has been trained and both the distributions are same. Any questions on this? Are you able to visualize this particular thing?
So, may I ask one question?
Yeah, please go ahead, Rajneesh.
So, as you had just explained, the generator will start generating images
Generator
based
will
on some
start.
model,
Yeah.
based on some model, and discriminator will get that image as one part and one image which already has from the data, and then it will compare and then give a feedback to generator. That's what I understood.
Yeah, true.
So if we see, sir, the generator is then modifying its weights again to generate some image which is maybe matching the discriminator based on the discriminator feedback. So, basically, it is still learning the probability distribution itself. So when we say that
Yeah.
in this case we will not be learning probability distribution, then how? matlab,
Okay. So what we said is we never said that we are not going to learn the probability distribution. What we said is we are not going to make the likelihood as our training objective. So that is actually our goal. So we don't want likelihood based training. So we don't want things like to use things like KL divergence to compare the two distributions. However, these independent components which are there, for example, your classifier or your discriminator, they are essentially learning the modifying the weights. But the objective that is there, but the training object, min max objective that we are training on this particular thing is not based on likelihood. This is not a likelihood based training. This is this is basically a training which is likelihood free. We are only taking the samples from the model distribution and the samples from the true distribution and comparing them. But inherently, under the hood, the discriminator is essentially a neural network which is fine-tuning itself to get the optimized phi, and the generator is fine-tuning itself to get the optimized theta. And ultimately, when we, I don't know whether I'll get to that slide today, but ultimately, when we go towards a few slides later, we are going to see the training in this particular fashion is equivalent to using some form of divergence, not necessarily a KL divergence. KL divergence is just one form of divergence. Here we will see that this will kind of become equivalent to some form of divergence. Okay, so remember one thing here. Remember one thing here. When you see this particular diagram, this. So in this particular diagram, the tool of choice for performance measure was KL. And we somehow knew that minimizing the KL is equal to maximizing the log likelihood. Minimizing the KL is equal to maximizing the log likelihood. And that is the reason why we were always interested in the log likelihood to essentially minimize the KL. Okay. Now here we are not even accessing this log likelihood, and there is no question of minimizing the KL. What we are going to do is essentially train two separate neural networks. One is the generator and one is the discriminator. Both of them are going to be trained together. And ultimately, the training objective function that we are based on which we are going to train it, that is this one, is independent of your likelihood. So that is the story.
Sir, sir, any computational advantage or anything advantages which we are getting out of why this shift has happened from like log likelihood, or these are just parallel cases to
No. If you have been following the first part of my lecture, what did I say? In the first part of my lecture, this is a case which we proved. Great test log likelihood, poor samples. Okay. Now remember one thing. Whenever we were discussing any type of models, generative models, be it autoregressive, VAE, normalizing flow, we always said that if we are able to somehow if we are somehow maximize the log likelihood, that means our learning is complete and we will now be able to generate good samples. That was the fundamental assumption, right?
yes.
But with this particular equation, what did we see? We saw that your model distribution, your expectation over your model distribution, the upper bound is equal to the data distribution and the lower bound is equal to the expectation of the data distribution minus log of 100, which is equal to 4.6. So there is a narrow difference between the lower bound and the upper bound. The difference is only 4.6 units. So what we what this what we suggested here in case one, we what we suggested here is that if under a theoretical condition, if my p theta is exactly equal to p data, then in that case, my sample quality, I have the guarantee that my sample quality will be the best when my log high, along with the highest log likelihood. But in reality, these two quantities will never be the same. They will be an approximation. Okay. If they are an approximation, then what happens is this particular thing is true. So now we have a model where we said that our model generates 1% of data from the true data, samples from the true data, and 99% from the noise. So 99% of samples come from noise. Now, when we did this particular derivation, we found that even with a 99% noise, even with a model which generates 99% sample from the noise, my distribution, my true data distribution is at max is going to be 4.6 units worse than the true data distribution. My model distribution at max is going to be 4.6 units worse than the data distribution. Now that means that we have a very narrow margin here. So that is the reason, that is one of the reason why great test log likelihood does not always translate to good samples. It does not mean, it does not mean that uh, um, great test log likelihood will not give you good samples. What this particular derivation is trying to prove is that these two are not tightly correlated or tightly coupled. Okay. You
Okay.
do not have the guarantee that if you have good test likelihood, you basically have you will have good samples. This is point number one. Point number two is whenever you are working with log likelihood, you have some constraints in your design. You have to design your architecture in such a manner that, or generative models in such a manner that you somehow have access to the likelihood, be it in the form of autoregressive or uh, uh, normalizing flow models, or you have indirect access to the likelihood, for example, in case of a VA. Okay. So that is actually a constraint that we have put. But with GAN, we are getting free from all these particular things. What we are saying is that we are no longer are in the likelihood learning zone. We are comparing samples. If both the samples are perceptually same, then it means that my model has done a good job. Both the distributions are same, and that is the incentive why we want to go towards scan. But at a later point of time, maybe in the next session, we will realize that even though all these things, I mean, there is a lot of potential in GAN, and GAN was the in thing at least during the Corona period. Okay. uh, Later on, kind of diffusion models took the stage. All right. And GAN took a backseat because of the reason that GANs are very hard to train. So you don't know when and when a particular when the GAN will converge, and then there is a problem because there is a min max game that is going on. It is very difficult to train a GAN, and there are a lot of tricks that are needed to train a GAN. So GAN gradually gave way to diffusion models. But the idea of GAN is very powerful, that you don't need access to the likelihood to do the training. You just need access to the samples, and you have a generator and a discriminator who are basically trying to fool each other and essentially and essentially give you samples which are I mean perceptually same as the original training examples. Got the uh, concept?
Yes, sir. Thank you, sir.
All right. It's this. Okay. So now this is my training objective. Okay, this is my training objective for a discriminator. Okay, even though this function has both the generator and the discriminator, for the time being, I am considering the discriminator as fixed. Sorry, generator is fixed. Don't worry about the generator. Okay. What I'm saying is I have a generator which is generating something. I'm not training the generator. I'm only want to train the discriminator first. I mean, theoretical case, just to explain the slide. Okay. So what I'm going to do is I'm going to maximize this particular function with respect to d phi. So basically, I'm going to d phi, I'm going to basically try to maximize. And this is my training objective. And if you can see, this is nothing but the cross entropy. Okay. So what does it say? It says that for a fixed generative model p theta, the discriminator is performing binary classification with the cross entropy objective. Assign probability 1 to the true data point, x coming from p data. Assign probability 0 to fake data points, x coming from p theta. Okay. Now let's talk about it a little bit. So this is my objective, which my discriminator is trying to maximize. Okay. Discriminator is trying to maximize. Now let's talk about it a little bit. Now what will happen is this objective function has two parts. First is this part. Okay. Now for real data, when x comes from the data distribution, we want d phi x to be close to 1. That is real. So we use log of this. And for fake data, x belonging to p theta, that is, we want d phi x to be close to 0, right? And so we use this. Together, this is nothing but the binary cross entropy loss, but from the perspective of the discriminator trying to maximize its performance. So that's what it is. Okay. So now the question is, what is an ideal GAN setup? What is an ideal GAN setup? Okay. Do I have a page here? So let's talk about the ideal GAN setup. In the ideal GAN setup, what will happen? The generator will become perfect, right? The generator will become perfect. Now, when the generator becomes perfect, what is going to happen? Sorry. So in an ideal GAN setup, when the generator becomes perfect, that means it is sampling in all the correct samples, and my discriminator is no longer able to distinguish it. What what happens is this particular term is going this particular term is going to be equal to half. Why? Because it is nothing more than a random chance, right? The generate discriminator does not know that whether it is a true sample or a fake sample, and it is fully confused, and its output is close to half. So this means that the discriminator is confused. It can't tell if a given sample X came from the real data or from the generator. Okay. Now, what does the optimal discriminator? What does the perfect generator? Why does it look like this? Okay. Now, if a generator, so this is case one. Case one. Okay. Case one is perfect generator. Now, in case one, in case of perfect generator, we know that P theta is equal to P data X. We have achieved this. In that particular case, what happens? Your this right? This is why it becomes half. This means that the discriminator gives 0.5 probability to every sample. It is completely uncertain. It cannot distinguish real versus fake, and the generator is now perfect. Okay. What happens in the other cases? In case two, what happens? Suppose the generator is poor. Okay, it produces values far away from the real data. Now, there can be two cases here. In regions where P data X is far greater than P theta X, what will happen? Your D theta will be equal to 1. That is very unlikely real. And the other case is going to be this. Your P theta X is much greater than P data X, and we get your D theta star is equivalent to 0, which means very likely fake. So this is very likely real. This is very likely fake. In both the cases, it is able to distinguish. So the discriminator can easily tell them apart that the generator is bad. So therefore, I mean, in an ideal scenario, the generated samples are actually indistinguishable from the real ones, and the discriminator cannot do better than guessing. And this is how GAN training is designed. So the generator wants to reach a point where the discriminator outputs 0.5 for all the samples. So this is what is happening. And if I go back to this particular slide, if you see, the optimal discriminator is this. Okay. And if we have already done the sanity check, that it cannot do better than chance. Right. So if we now go to this, now comes the second component. Okay, till now we were talking about the first component, even though we gave you the flavor of, I gave you the flavor of the second component just to make sure that all the things are in place. So now what will happen is this GAN is nothing but a two-player min-max game between a generator and a discriminator. The generator is going to be a simple neural network, where, I mean, where you are, I mean, it is deterministic in nature, and this G theta is the neural network, which takes any Z, which is basically any type of noise or any random sample and converts it into X, a sample, right? So you sample from PZ, which is a simple prior Gaussian, and you get your X. The only difference is that this does not need to be invertible. So you get a little bit more flexibility. It does not need to be invertible. Why? Because we don't want to go towards Z. Okay. So distribution of Px over X is implicitly defined, no likelihood. Okay. So now you see that even though, I mean, even though the distribution over P of X over X is implicitly defined, we never use the likelihood, and minimizes a two sample test in support of the null hypothesis. So you remember your generator, sorry, discriminator. What was your discriminator trying to do? The discriminator was trying to maximize the test statistics in support of the alternate hypothesis, which is P data not equal to P theta. Right? That is what the discriminator was trying to do. It was trying its best to distinguish between the samples. And what the generator is trying to do is it is trying to do the opposite. It is trying to minimize a two sample test objective in support of the null hypothesis, okay, which is P data is equal to this. All right. So you now see that we are no longer bothered about this particular quantity, which is essentially P of theta x. As we would just want to sample, we don't need the density. We just need the sample. We just need the sample. All right. And as we are sampling, my neural network parameters are, I mean, as we are sampling and iterating, my neural network is getting optimized and my probability distribution is changing. So that is what is happening under the hood. Okay. All right. Now, one last bit from before I end this class is, what is the training objective of the generator? Now, this max was the training objective of the discriminator. Now we have a mean. The same expression, we have a mean. Okay. Now this is the training objective of the generator, and together it is the training objective of the GAN. All right. So now let's talk a little bit about this particular thing. Yes. Okay. All right. Now the question is that how GAN training objective connects to divergence minimization. All right. So let's talk about the GAN training objective. The GAN training objective that we have seen is this. Mean of the generator, max of the discriminator. This is the function is equal to expectation of X from P of data. We sample from P of data to calculate the expectation, and log of D of X plus expectation of X when you sample from the generator, which is this G, and log of 1 minus D of X. This is my objective function. Okay. Now, for the time being, I keep my discriminator. I say that I have already done my training and I have the optimal discriminator. Okay. I have the optimal discriminator. So the optimal discriminator this is the optimal discriminator. Now, what we are going to do is we are going to now we have an optimal discriminator. Okay. All right. Now, for the optimal discriminator, what we are going to do. Okay. So we are going to write this equation. And I'm going to write this d of x. All right. This d of x as this p of data x by p of data x plus the generator. Okay. From the earlier slide. And the other one would be x p of data x plus p of g x. This is the other one. Okay. Now what we can do is once we have written this, what we have written this, what we can simply do is I'm not going to again write this entire expression. I can do this. Does not matter, right? If I can do this, then I can easily say that this is going to be log of p data x divided by p data x plus p of gx divided by 2. Okay. And I can easily write this, the same thing. So this obviously this is an expectation. This is an expectation here. And there is another expectation here with respect to G. I'm just writing it. So this will be log of P data X divided by P data X plus P of Gx divided by 2. Okay. And now we had this half on both sides. This is basically a log, right? I can write it as a sum and then I'll flip the half and this will become minus log of 4. Okay. Now, what can we write here? Now we can see that this is nothing but a KL divergence between P of data and this particular quantity, right? So I can write this quantity as DKL P of data and P of data plus P of G divided by 2 plus DKL P of G P of data plus P of G divided by 2 and minus log of 4. Now we have talked only about KL divergence. There is a lot of divergences that are available. One such divergence is called the Jensen-Shannon divergence. Okay. Jensen-Shannon divergence, JSD, between P data and PG is equal to half of DKL into P of data Okay, this is basically the formula of Jensen-Shannon's divergence. And now, if I just plug in this formula at the top, what will you get? Your basically GAN training objective is equal to twice of JSD, P data, PG minus log of 4. And now you see an important thing here. What does it mean? Where is it? Okay. What does it mean? It means that the JSD, I mean, see, the JSD measures the similarity between two distributions similar to KL. The only thing is that it is symmetric in nature. Okay. The value function becomes small, that is minus log of 4, only when the JSD is 0. Okay, that is the generator distribution exactly matches the real data. It becomes minus log of 4. So minimizing this particular objective function is equivalent to minimizing the JSD between the real and the fake distribution. And that is the reason why, even though we are taking an approach of not using likelihood, but fundamentally we are performing divergence minimization, even though we have never said it explicitly. Okay, so we never said that we are doing a divergence minimization, but now with all these derivations, you are seeing that whatever we are doing is essentially translating to some form of divergence minimization. However, in this case, it is basically the what you call the Jensen-Shannon divergence. And this is basically, so you can see for the optimal, if you see this last line, for the optimal discriminator, which is D star G and generator G, we have this particular thing is equal to minus log of 4. Okay. And this Jensen-Shannon divergence, also similar to KL, has these properties, which is it is always positive. Okay, positive, or it is 0 when P is equal to Q. All right. And unlike the Jensen-Shannon divergence, unlike the KL divergence, here what is happening is essentially this is symmetric in nature. So KL divergence of P and Q is not equal to KL divergence of Q and P, but in this case, this is equal. Okay. Now, any questions till now?
Sir, why we have only divided by 2? Is there any, or we can take any number for that?
Which one are you talking about? Can you tell me?
When we were deriving the
Okay. We took 2
yes,
because
sir.
because because of the fact that the formula for JSD is this. Let me show you a better. This is the formula for JSD. In JSD, you see that it is the half of KL divergence between P and P plus Q by 2 plus KL divergence between Q and P plus Q by 2. Now we have to somehow bring these two in the equation. So that is the reason why what we did is we essentially multiplied by 2 and divided by 2 so that basically we can get this particular 2 without impacting anything, because 2 and 2 will cancel out. And that is the reason why at the end, we got a minus log 4, which is basically when both of these quantities are equal.
Okay, sir. Thank you.
Okay. All right. So now, okay, we have 20 minutes left, but I don't want to go any further. Okay. We have discussed a lot today. What you need to understand here, and I'm just going to talk you through this. See, when you go through the GAN literature, this is only uh, I mean 25% of the 25% of what you need to understand is um, key things for you to take away from this particular session is that why we want to move away from likelihood based training. The reason why we want to move away from likelihood based training, because we saw that at best, my likelihood is going to be equal to the true data model. Likelihood of the model distribution is going to be equal to the true data distribution. But in the worst case, it is only going to be 4.6 units less than the true data distribution. And this is only, I mean, when we take a single dimension. Okay. Now, if you take multiple dimensions, what will happen? This 4.6 will get divided by the number of dimensions and it will become very less. So somehow we saw that even though we always said that so the margin or the maneuvering space is very less. Okay. So somehow when we were talking about probability density or likelihood based training, we always thought that likelihood, if we are able to get the maximum likelihood, we will be able to get good samples. And there was a direct correlation between the two. But then now we realize that this is not always the case. The only case when this is true is when your model distribution is exactly equal to your true data distribution, which will never be the case in real life because you will never be able to get the exact distribution. There will always be a margin of error. If there is a margin of error, if there is a margin of error, then this particular property kicks in, where essentially you see that with a 99%, even with a model which has 99% noise, the um, the model distribution is only 4.6 units below the true data distribution. Okay. And then the reverse case also we saw is overfitting case, where the model memorizes everything and now we get very good samples, but our likelihood has gone for a toss. Okay, because of the memorization problem. So it is, and also from the previous lectures before pre-midsem, we saw that whenever we were training any of these likelihood-based models, we always had to take care that we had access to the likelihood, or we had some access to some lower bound of the likelihood. Okay, and that itself had made some constraints on the design. With this approach of likelihood free training, what we are doing is, and before I go into this, you remember that in this likelihood based training also, the ultimate goal was to reduce the KL, I mean divergence. Okay, I mean some form of distance. All right, some form of distance in the form it was KL divergence in that particular case, because minimizing the KL divergence is equal to maximizing the likelihood. Now, what we want to do now is we want to go away from this likelihood based training, and we want to use some other performance measure. But ultimately, this performance measure will also, as we have seen, will also implicitly be for some form of a divergence minimization. Okay. Mm. So that is the reason why what we said is, if we can have a discriminator if we can have a discriminator, so because of this, what we did was we came up with a GAN setup. The GAN has two neural network. One is the discriminator, which is nothing but your classic, classifier. Uh, it is a neural network, and its job is to try its best to discriminate between the samples coming from the true distribution and the samples coming from the fake distribution. Okay. And then we also have a generator, which is basically whose job is basically to generate these fake samples. Okay. So this is also a neural network, and it's a deterministic neural network, but at the same time, it does not need to be invertible because we don't need to go the other way. So what we do is we pick a noise, we pick Z from some distribution, some simple Gaussian distribution, and convert it into a sample. And then my discriminator tries its best to basically distinguish between the two samples. Now, this particular training goes on iteratively, where every time the generator is trying its best to generate a sample which will fool the discriminator. So the goal is that my discriminator should reach such a stage that it always outputs 0.5, because 0.5 is nothing better than the toss of a coin or chance, right? So if it is maximally confused, that means my generator has done a good job in learning the distribution, true distribution. And this is the min max game that goes on. And now when we did a slight derivation of this training objective, we saw that even though we never said explicitly that we are working with any form of divergence or anything, but ultimately we saw that this is equivalent to minimizing the what you call um, I mean, uh, we are fundamentally performing divergence minimization, even though we never said this particular thing. And you're minimizing your objective function is actually minimizing the Jensen-Shannon divergence between the true and the fake distribution. So this is the build up to the machinery of GAN. Now, what we'll do in the next class is essentially we are going to talk about a little bit about why GANs are hard to train. And that is the only reason why GANs have fallen out of favor. Okay. So we'll talk about why GANs are hard to train. And then we will go to some more advanced concept, some more advanced concept. And probably we'll need 1.5 class more to finish GAN. Now, remember one thing, and the last thing that you need to take away from the class is that when we talk about GAN, there are various types of GANs. Okay. BiGAN, DigiGAN, and all those type of GANs. So what I would suggest is from these two lectures or 2.5 lectures, try to get all the fundamentals correct for GAN, and then you can basically go through the GAN literature. I'll upload some research paper as well, and on a research article on GAN. You can go through it if you are interested. The whole idea is that your fundamentals needs to be correct, and then you just need to get a flavor of why DigiGAN is used. What is the advantage of DigiGAN over BiGAN and all those particular stuff, standard stuff. So you can go through that. So for now, we'll kind of conclude the lecture here, unless and until you have any questions. Okay. In case you don't have any questions, then and we'll close the call for today. Thank you, everyone, and then we'll meet up in the new year. Thank you.